Okay, so this is the course on the introduction to complex numbers. So here's my notation. Okay, I'm going to use this character to mean the real numbers. And I'm going to use this character to mean the complex numbers. Okay, so let's get going. So what does something belonging to this set C mean? Z in C means that Z is equal to A plus I times B, where A and B are real, and I squared is minus 1. Okay. This guy here is called the real part of the complex number, and we usually write it as Re of Z. And this real number here is the imaginary part. Oop. Which you usually write as Im of Z. So let's just look at some simple properties. So first of all, if we have two complex numbers, here's one, A plus I times B, and here's another one, W. This is W or omega, I can't write the difference, so it's always the same. C plus I times D, okay? So here, necessarily, by what I've just said, A and B and C and D are real numbers, okay? Then what's Z plus W? That's just equal to A plus C plus I, B plus D. Okay, so you add complex numbers in a very simple way, and you notice that this is also equal to W plus Z, because you know that the order in which you add two real numbers together does not matter. Okay? And what's Z times W? And in common with most other mathematicians, when I don't put anything between two objects, it means I'm multiplying them. Right? I will not put dot, I will not put times, I will just leave a space, leave nothing. Right? So Z times W is, well, A plus I times B times C plus I times D. And now we just expand this in the usual sort of way. So this is AC, and because I squared is minus 1, it's minus BD. And then we have the cross terms, I into, and I'm going, which one am I going to write first? AD plus BC. Okay, so that's the product of two complex numbers. And you notice also that this is actually, you can work out for yourself, this is the same as W times Z. Okay, so what about Z divided by W? Okay, so for this we have to note that if I take W and I multiply it by this guy, well, I put a minus sign in here. Okay, then this, by the definition of the product here, is C squared plus D squared. Okay, because the cross terms cancel. And this, you'll notice, is a real number. So these were clearly complex numbers, right? But this is a real number. And so then if we want to do the division of z by w, well, this is equal to a plus ib divided by c plus id, and then we multiply this by 1. Okay? I'll put these in brackets so there's just no ambiguity here. And we multiply this by 1. C minus id over c minus id. Okay? And now I can multiply the bottom line, the denominator, and get that this is equal to, and I'm no good at these things, so AC plus BD, I guess, and therefore divided by C squared plus D squared. That's the real part, and the imaginary part is equal to, I'll write it this way, BC minus AD, is that right? BC minus AD, that's right, divided by, again, the same denominator, C squared plus D squared. Okay, this D. Okay. And this is true, of course, provided that W is not 0 in the complex numbers, which is obviously in the real numbers 0 plus I0. Okay? So as long as W is not 0, then C squared plus D squared is clearly a positive real number, and so we can actually divide. Okay? So that's some simple things, and in general, this is a fairly useful property, I guess. In general, Z equals W, this is the equality of two complex numbers, if and only if A equals C, the real parts are the same, and B equals D, the imaginary parts are the same. And what this has the consequence is that you can equate real and imaginary parts. Okay. Can everybody see this? I'm looking at the people on the back row, especially the person over there who doesn't see it. Can you see this? Okay. And you can hear me? Okay. Okay. Okay, so in this here, we have made use of the conjugate. And what's the conjugate? The conjugate is something we write as Z bar, right? And Z bar is A minus I times B. So in other words, if Z is A plus IB, Z bar just changes the sign of the imaginary part, and we note, as we've seen above, that Z bar is real. Okay? And it's also non-negative. Okay? So the real part of Z is equal to Z plus Z bar over 2. That cancels off the imaginary parts, and the imaginary part of Z is right, you're listening good. Z minus Z bar over 2i, right, okay? I'll just carry on here. And further, the following are true. For all z and w in the complex numbers, z plus w bar, right? So this is z plus w is a complex number, so you can take its conjugate, and this turns out to be the same as z bar plus w bar. That is, you can conjugate and add, or you can add and conjugate. zw is a complex number, you can take its conjugate, and this is equal to z bar w bar. Okay, perhaps I put those a little too far apart. There we go. You can conjugate and multiply, or you can multiply and conjugate. You get the same thing. And z over w is a complex number. You can take its conjugate. This is z bar divided by w bar when w is not 0. Okay? So you can go away and prove these. These are a simple exercise for you to go away and prove. Okay? Okay, the need for complex numbers arises from polynomials. Okay, so for example, if I have a polynomial, right? So here's a polynomial of argument, and I'll call the argument x. That's all right, isn't it? Is equal to x cubed, so this is a cubic polynomial, plus 2x squared plus 2x plus 1. So there's a cubic polynomial, all right? Okay. So this, I claim, satisfies that p, if you evaluate at -1, then this is a 0, because 1 minus 2 plus 2 minus 1 is 0. Okay? And so that means I can write p of x is equal to x plus 1. That's telling me that it vanishes when x is -1. And then I have to find out what's the remaining term. There must be an x squared to give me an x cubed. There must be a 1 to give me plus 1. And I think there must be an x to make sure that the other two terms work. Right? Okay. And so what do we see? We see the other roots of this polynomial satisfy that x squared plus x plus 1 is 0. And we know how to find the roots of a quadratic. We can simply apply the formula, and so the roots are, well, they're minus b plus and minus the square root of b squared minus 4ac. That's 4 times 1 times 1 all over 2a. Okay? This is equal to minus a half plus or minus I times root 3 over 2. So the roots are necessarily complex in this case. I squared is -1, as before. So this simple example illustrates several things. Okay, that are generally true. Things that are generally true about any polynomial. So I chose specifically a cubic there, but there are several things that any polynomial will satisfy. Okay, so let me write a general polynomial, and this time I'll write it in terms of an argument z. Okay. This is a0 plus a1 times z plus a2 times z squared and so on, plus an times z to the n. Okay. Here n is an integer and it's bigger or equal than 1. These aj's are complex numbers. Okay. And this is true for j equals 0, 1 up to n. Okay, so this is the way we usually think of polynomials. We'll see them in this course in many, many, many different forms. But this is perhaps the way that you've seen them most simply written down before. Okay. So what are the things that are true? The first thing is the fundamental theorem of algebra. I am going to quote this for you. I am not going to prove it to you. You need a lot more mathematical machinery to be able to prove this. And you'll learn that mathematical machinery in the next few years. Okay? And here's the fundamental theorem of algebra. And this says that P of z is equal to a sub n, that's this guy, times z minus, and I call these gammas, z minus gamma 1 times z minus gamma 2 times z minus gamma n. Okay? For n complex numbers, gamma j. Right? Right? I've said it twice here, right? Written in words and written it down here in mathematics. So that's right, and this is for j equals 1 up to n. In other words, every polynomial with of degree n, which the highest power is z to the n, let's say, has n complex roots. Right, so that's the fundamental theorem of algebra. That's the first result. Here's the second result. I just don't think this has a name, so I'm just going to call it a theorem. So if these aj's are not complex at all, well, they are complex, but they're also real. Okay. If the aj's are real, okay, all of them, then, and I'm going to use this character a little bit. This character means there exists. It's not just me that uses this character. You'll see it a great deal. Many of my colleagues will also use it. Okay? Then there exists a number r with 0 less equal r less equal n with the following being true. P of z is equal to a sub n, again the same guy as here, the same guy as there, times z minus alpha 1 times z minus alpha r, this is this r that exists, okay, times q1 of z times qs of z, okay, where r plus 2s is equal to n, okay, where also the alpha j's are real, right? up to r. There's r of them. And the term qj of z is precisely a quadratic polynomial. Z squared plus bjz plus cj. So quadratic polynomial with a coefficient 1 here. Okay? So in this case, bj and cj are real numbers. Okay? And these things are also equal to z minus gamma and z minus gamma bar. So this is the conjugate of this guy. Okay. No, sorry, gamma and c, that's right. Okay, and this is all true for j equals 1 up to s. Everybody can see this. I'm sorry, I put it in the shadow. But, all right? I'm not trying to hide it. This is the conjugate. So you can write down any polynomial that has real coefficients. It may have a number of real roots, either between 0 and n of them. And then it has the remaining terms, which are also can be written as real polynomials, real quadratic polynomials. And those real quadratic polynomials have two complex roots, which are conjugates of each other. And you can see that in the example above, right? Minus a half plus and minus I root 3 over 2. That's a complex root times its conjugate. Okay? Okay, so I'm just going to write one more thing down here, which is a consequence of this. Thus, if all the coefficients are real, okay, and gamma being a complex number is a root of p, okay, then gamma bar is also a root. A p. You can see your disadvantage now. You can't do anything about this. Okay, we've done that. So then we come on to the polar form. Okay. And the polar form is like the following. I can draw a picture. And this picture has the real axis going out this way and the imaginary axis going up this way. That's the usual way it's done. Maybe on some other planet they do it the other way around, but we don't. We do it like this way around. Right? Then I can put down here the real part of a complex number. Here, z is equal to x plus iy. And this is the real part, is the abscissa, if you like. It's the x coordinate. And here's the imaginary part over here, and this is y. Is the imaginary part of z. Oh, right, that's very well. Okay, so that's this number here. This is just supposed to be a broken line that indicates that's where x plus iy is. But we know that points in a complex plane you can also represent in polar form. So if I draw a straight line between these two things, I can write the distance of this point from the origin as r, and this angle here as theta. And this would be the polar representation of a complex number, z equals x plus iy. So r is equal to the square root, and I shall emphasize it by saying plus, the square root, right? It's the positive square root. It's a distance. It cannot be negative. It's plus the square root of x squared plus y squared. And this is called the modulus. This is the modulus of z. And it's usually written as this. And, oh, this is a very much thinner one. And theta is the inverse tan of y over x. I don't know why I need a bracket here. I don't really need a bracket. This is the inverse tangent of y over x, okay, is the argument. Okay, it's the argument, and I sometimes put an e in, but I don't think there's any e. It's the argument of z, and this is written as, well, usually different things in different languages, but usually this. That's what I shall use. Okay. So the first thing to note is that the argument is not defined. The argument is not defined for z, which is the 0 complex number. R is perfectly well defined. But I think that's the only complex number for which we cannot define an argument. Okay? So you notice that if y is positive and x is 0, then argument of z is just pi over 2. Right? And if y is negative, these are real numbers, right? So I can say this, and x equals 0, then the argument of z is 3 pi over 2. Okay. And also clearly theta plus 2 pi, theta minus 2 pi, theta plus 4 pi, etc., right? You see what I'm doing here? These all define they all define the same argument. That is, if you give me an argument of theta plus 18 pi, that's exactly the same argument as the number that has theta as its polar angle. Right? I should just tell you, if 0 is, and I think less equal theta, and this is less than 2 pi, okay, then this is the principal argument. The principal value. The principal value for the argument. Okay, so we can write a polar form. I'm sorry, standing back, I realize that my straight line from the origin to z equals x plus iy looks slightly curved. I'm sorry, that's a human fallibility. We can't draw exactly straight lines. It's supposed to be a straight line. Okay. Note that z bar, the conjugate of z, has modulus r, right? It's the same as the modulus of z. It's the same distance from the origin. Right? And argument minus theta. Okay? That is, if you look at the conjugate on this diagram here, the conjugate is somewhere down here, right? And so the angle is minus theta. Okay. Oh, not too much. Also notice that you can write x is r cosine theta, so this is just trigonometry. Okay. And y is equal to r sine theta. Okay, this is just to express. This expresses x and y in terms of r and theta. Okay. Okay. Here's a proposition for you. I claim this is true. Right. For all z and w in the complex numbers, we have that the modulus of zw is equal to the modulus of z times the modulus of w. I'm not claiming that's immediate, but I'm telling you it's true. The modulus of z over w is the modulus of z divided by the modulus of w, and this is true, of course, if w is not the zero complex number. And the modulus of z squared, that's just the square of a real number, is equal to z bar. So I claim that those things are all true. I also claim that the argument of zw is equal to the argument of z plus the argument of w. Okay. And this is true, of course, when z isn't 0 and w isn't 0, because the argument's not defined if either of them is.
I thought the codomain of the inverse tangent was...
He's trying to be smart, notice? He's showing you that he's listened to the lecture this morning. The codomain of the tangent, right?
Yeah. Shouldn't it be between negative pi over half and pi over half?
It's up to you. It's up to you. So I can choose, and probably on the planet Zog they do, choose the codomain of the inverse tangent to between 17 pi and 19 pi. It makes no difference at all. It's up to you. You can either decide to be between 0 and 2 pi, that's what I'm doing, or you can decide to be minus pi and pi if you wish to. It's not going to, you're being formulaic here. This is not mathematics. It's not going to change the way mathematics works. But if that's what you were taught, then open your mind and be flexible, right? Some of what you were taught at school is probably sort of true, right? What I'm telling you here is true. And I'm not being arrogant. When you start to do analysis, you will see that we have to be very, very precise to make sure we can have firm foundations. So you may think this lecture is very simple, but it's also correct. That's your first, that should be stage 0, that should be what you desire, right? So it's correct. But thank you, I do appreciate interruptions. This was not foolish, I'm sorry I didn't need to put you down at all. Thank you. All right. So the argument of ZW is the argument of Z plus the argument of W, and the argument of Z over W, okay, is equal to the argument of z, oh, brackets, minus the argument of w, okay? Okay, and again, I need both z and w to be non-zero, not just because I can't divide by a zero number, but because the arguments are not defined. These two numbers are not defined if either of them is zero. Okay? Okay, so that tells you some things, but you notice I didn't tell you anything about the modulus or argument of z plus w. And here we have to go into inequalities. And this is called the triangle inequality. Okay. Okay, the triangle inequality tells you that if you have z plus w and you take its modulus, then this is no bigger than the modulus of z plus the modulus of w. So you don't have, you like inequalities, I know. When you're at school, you like everything to be this equivalent and so on. Right? But this is not true, right? Z plus W is not equal to Z mod Z plus mod W. But it's always smaller than that. This is called the triangle inequality. And you can go and persuade yourselves by drawing pictures of triangles why this might be the name given to this inequality. Okay? So, as I claimed was a proposition, for proofs, okay, I'll leave these for you as an exercise. I've told you plenty to work these out, or you can see some of these statements. You can see the outline notes, see the online notes. Okay. So there's independently written online notes written by my colleague Richard Earle, which you can find on the website for this course. I put them up, okay. And you'll find some of the proofs written there. But let me just end this lecture with just a few of these proofs of the things that I've said today, okay. So, for example, these are just examples of some of the proofs that we would need. One of the things I claimed was true was that ZW bar was equal to Z bar W bar. I claimed that on the middle, I thought it was on the middle board. Where did I claim that? Somewhere. You can see the board. I can't see the board from down here. That's the problem. Right, anyway, I claimed this somewhere. Well, here's a proof. Z is equal to A plus IB. Okay, and W, oh, we don't need W, do we actually? Oh, yes, we do. Yeah, W is C plus ID. Sorry, yes, we do here. Right. Okay. And so what's ZW? ZW is equal to AC minus BD, right, plus I into AD plus BC. Okay. And so if you want to take the conjugate of this guy, we change this, right? We change the sign of the imaginary part. And then what's Z bar times W bar is A minus IB, that's Z bar, times C minus ID, that's W bar, and that's equal to AC plus BD, is that right? So why did I get a minus here? It's minus. Oh, I squared is minus 1. There you go. Good. Some people are awake. This thing's in, right? AC minus BD, and then we have. Tell me again if I'm wrong. I have a minus I times AD plus BC. Oh, and that's the same as this. Right, so that's your proof. Oh, and I'll prove another result that I quoted on the board there. Let's suppose that I have gamma in C, okay, and a polynomial P of gamma is equal to 0. Right? So gamma is a complex root of a polynomial. Okay? Okay? Then I certainly have that P of gamma bar is equal to A0. This is my same polynomial I wrote down there, plus A1 times Z, gamma bar, plus A2 times gamma bar squared, plus A n times gamma bar to the n. Okay? I'm proving this way here. Okay, so this is this. Okay. And so if the AJs are in fact real, okay, if the AJs are real, J equals 0, 1 up to n, so all of the coefficients are real, then this means, of course, that AJ is equal to AJ bar. It's pretty conjugate of a real number is itself. All right. So P of gamma bar is equal to, well, instead of A0, I can write down A0 bar because that's the same number. And instead of A1, I can write down A1 bar times gamma bar, that guy, plus A2 bar times gamma bar squared, plus AN bar, gamma bar to the n. Okay. But now, what have I told you about taking conjugates? I told you that the conjugate of a product is the product of the conjugates. And so I can write this as A0 bar plus A1 gamma bar. Right? And here's just a product. Got 3 items in it, but they're just product. So this is A2 gamma squared bar. Okay? Plus AN gamma to the n bar. This is a product of n plus 1 items. And each of those products, between 2 things, I can apply my rule that the product of conjugates is the conjugate of the product. Okay? So this equality here is using the properties above. Okay? And this is equal to, well, hang on a second, this is the modulus of a complex number plus the modulus of a complex number. And the modulus of a complex number plus the modulus of a complex number is the modulus of the sum. On the top there, right? Conjugate, oh gosh. The top result on the board up there, Z plus W bar is Z bar plus W bar. Right, so this is equal to A0 plus A1 gamma plus A2 gamma squared plus AN gamma to the n bar, right? That's just using the result at the top of the board there. Many times, but a finite number of times. Right? And so what's this? This is P of gamma bar. And that is the conjugate of 0, because P of gamma is 0. And the conjugate of 0 is 0 minus I0, and that's the same as 0 plus I0. So that proves this for you. For you people over there, that proves this result for you. Right? Don't sit there tomorrow. Right? I can't do anything about this. I can't knock this thing away. Okay. So tomorrow I will carry on with this simple excursion into complex numbers, I suspect that many of you have seen quite a lot of this material before. Perhaps not presented in exactly the way that I'm presenting it. Perhaps so. I don't know. It doesn't but yeah. So I'll see you tomorrow morning. Okay. No. No. This is my job. Right? This is my job. I'll let you applaud my lectures if and only if, when the council worker comes to empty your dustbins, you clap them while they do their job. Okay? This is my job, so please, do this.